refer to it for academic purposes, reference.
I think we are also. Like social media team, our social media team created in their Astro Club.
Good afternoon, everyone. I am Bhumika from Astrophysics Physics major. I am extremely delighted to introduce our next guest speaker, Dr. Parisee Shirke. Standing in the top 1% of the Maharashtra Higher Secondary Board examination, she received an advisory note for taking pure sciences as a career. Accordingly, ma'am became an alumni of our college, totaling 7 years of education in physical sciences, mathematics, and statistics. She cleared mathematics and statistics. She cleared the IUCAA National Admission Test (INET) in 2017, appeared for the PhD interview, and excelled. She got her PhD awarded by the Jawaharlal Nehru University. She is eligible for the prestigious DST Inspire Fellowship for continuing postdoctoral research. With All India rank of 34, she is a UGC CSIR certified physics lecturer. She is also certified as an endorser for the Archive Open Access Research Database. Recently, she stood as a reviewer for the American Astronomical Society. Along with her academia, she is engaged in science communication through a YouTube channel, Life Around Science and Miracle. Do check it out. She is an active and leading high-energy astrophysicist. So, without any further delay, I would like ma'am to take over the stage and give us a glimpse of the Indian space astrophysics.
Am I audible to everybody?
Yes.
So, without further ado, I will get right to the content of the talk. Over the course of the past few years of my doctoral work, when I have been at IUCAA, I realized that I was one of those few doctoral students who seem to have a heavy undercurrent of space-based astrophysical specialization throughout my coursework and also in my research. When I went through my files and folders on the information I had, it was pretty extensive. So I've tried to narrow down the scope specifically to Indian space astrophysics to keep to the time constraint over here. Another thing I've done is primarily the content I have put already in the slides and the presentation. So if you have any questions regarding that, I can further elaborate in the Q&A. What I will do through my speech is provide a brief overview across everything, and then we can see where somebody might be interested and I can go into the details accordingly. To clarify what I will not be covering, first and foremost, because space is a very general frontier. I will not be covering space missions that say get classified as interplanetary expeditions, for instance, like anything that is get sent to Moon or Mars, for instance, or even something like the Voyager mission, which is just sent out into the solar system. I will be specifically speaking about those missions that remain close to the Earth in orbit, or like the Aditya L1, which is again goes to the Lagrangian point and stays orbiting over there. And their primary motivation is to observe the sky around us, like we would not have been able to using a ground-based telescope. The most key word in my abstract is being able to provide a working glimpse. Because I'm not a faculty member, I will not be presenting to you the grand truths of the universe or something. I'm in a position to present to you. However, on the other side, um, some updates on what is happening in the ground reality, like what research is actually happening, being done right now, because it is a good balance of what can be done and also what needs to be done. So I'm slightly on that end because I'm the youngest speaker, I think, in today's uh, in the entire FIP. So I will be slightly different in this particular way. Now, space basically is any way if you think about the third dimension, geographically speaking, then deep sea and deep space become the natural frontiers in geographical physics, if I were to call it. Um, Space, not all countries are enabled in space right now, as you will see again along my presentation. So, apart from being a natural frontier, if you're able to do terrestrial physics, then going to space is something that very few countries are capable of. So, secondly, in astronomy, there are few observations which can be done from ground, but some parts of the electromagnetic spectrum require you to go into space. So that has been a driving force behind the development of space-based endeavors. Like I mentioned before, a lot of astronomy can still be done from ground-based telescopes. The necessity to go to space is because you get to see clearer images, for instance, in those bands which can be done from ground as well. So they provide you clearer, more magnified images. It's like if you're sitting at the bottom of a swimming pool and then trying to image, or whether you come out of the water and then image. So that kind of a difference is there. Still, whatever ground-based facilities we do have, they are being upgraded right now with active adaptive optics. So some of this work you will heavily encounter if you were to go out into trying to do astronomy in today's age. The ground-based ones are being upgraded with gear. And otherwise, the entire community is looking at space as the next thing anyway that doesn't present any of these issues to begin with. Again, something that I would like to touch upon in the beginning and then move out of this zone for the rest of the presentation. The Indian frontier still lags behind the international frontier as far as space is concerned. So India has been a new entrant in this field, but it has been a very promising, strong entrant in this field. And while there have been other space missions also recently launched, so I do have some fellow students who you will see some conversations on this front as well, but like I mentioned in the beginning, for the sake of brevity, I've narrowed down my scope to Indian physics. Because unlike the international frontier, the Indian frontier was slightly dormant up till this point, but it's fast picking up speed. Again, with these telescopes, you can do astronomy. So some of these telescopes, just because it's a space telescope that has been launched into space doesn't mean it's astronomy. So a lot of them, again, you can do a lot of physics with them. If it's a space-based telescope, then the international community also expects you to do a lot of physics, astronomy, astrophysics, and come out with a lot of those science-based papers using these telescopes. So what advancements you made in the pure science field, basically physics and astrophysics, using a space-based instrument. Okay, so to begin with now, Indian space astrophysics. I will divide the talk into two parts. The first one, I will give you a top-down approach of what the Indian space astrophysical frontier looks like, and in the second part, I will, because this is a student-based seminar and it's not a general talk, I will give you an idea about where our education lies and can contribute to this frontier and what might be expected from the student front. Because there can happen to be a disconnect between the two. What we see in the textbooks doesn't look as flashy, and what we read in the news seems a bit out of reach. So first, space-based research remains a way to establish a country as a soft power in today's age. Demonstration of space-based capabilities, that is, if you are able to do for astronomical research studies, remains a very constructive exhibition of one's power and can only give rise to healthy competition, if not engender a sense of awe, admiration and respect among all the countries around you. Some recent heroes that astronomy, the Indian astrophysics community was able to put forth AstroSat was conceptualized somewhere in the 1990s but was launched only in 2015 after a lot of planning. A good thing about AstroSat is even in their first pilot attempt, they were able to succeed, show a lot of science that has been done with the system by the science community, and they were also able to carry out work with AstroSat which is internationally relevant again. So that goes to show the kind of foresight you require when planning all of this well in advance of time. There are members over at Ayuka who have heavily participated in this, but it's not restricted to Ayuka. This is all over the astronomy and astrophysics community, and it remains a long-term, coordinated, collaborative effort. One of the main highlights, of course, remains the Shanti Swarup Bhatnagar Award, which is known as the Indian Nobel Prize, that was awarded to one of a discovery that was made with AstroSat, but it got published in a very internationally renowned journal, I think it was Nature. So that again goes to show that even though it was a pilot attempt for us, it was also, they are able to and they are trying to do work which remains internationally significant again. To give you a very recent update of where the community stands right now, this is an image of the high energy astrophysics community. High energy is the X-ray band. X-ray band is necessarily space. You cannot do X-ray observations from ground, which is why they are the first people to come forward whenever space is okayed by the government. So, this REDCO conference is an annual event, and if you see here, that one of the highlights is a special session on AstroSat and ExoSat, where they will be, where all the key people in this field will be coming together and delivering these talks on where we are right now. So that is again a very frontier in this field where we are right now. As far as my thesis is concerned, going back to the student front, recently I submitted into the AstroSat Physics PhD thesis repository. So all the theses or science which has been done with AstroSat, there's a common report website which is maintained for record. And it now, I think on Monday, my thesis got featured on this website as well. So there are like total 35 PhD students in India who have been able to do science with AstroSat. This is something that is shown to the general public on National Science Day. I have included here for the sake of completeness, but I will be providing more detail given that this is a student audience, not a general audience. But again, to give you an idea about where space-based astronomy is right now, some international telescopes along with a focus on the Indian one. So far, we would have had to discuss it would have only been the international front, but now if you see there are 3 AstroSat, Daksha and ExoSat. There are 3 from the Indian front now, which India has been able to get approved and show enough capability that they will be practical for launch. One which I wanted to highlight still was the NICER mission. You will see a lot of grad students using some of these as well in their work. I personally, my interaction with my involvement in the NICER mission, like some of them use the data or something. I was recently asked to review one of these papers which was being put forth regarding the NICER work. So you can contribute to all of these in different capacities. Not everybody has to be very in. There are different capacities in which everybody ends up contributing to each one of these missions. It's hardly ever a silo where you just stick to one thing and then are not expected to contribute anywhere else. I will again be drawing heavily from the work which I defended in my PhD thesis very recently. One of the problems, if I were to give you an idea about again what work is happening and what are the open problems right now which people are trying to deal with. This is a pencil or time degeneracy. My specialization has been in pulsars. So in pulsars, one of the main understanding of pulsar is it's like a lighthouse whose beam rotates in the sky, and that's how you see a fluctuating pulse when you observe it in the X-ray sky. This is a major problem in pulsar physics, which is the reason why I'm including it right now. It's known as the Fergusson College degeneracy, and it has remained unresolved for lots of years now, for about 5 decades. But now people are going to try to resolve this with upcoming missions which will be coming up. I personally, as an observer with X-ray space missions which will be upcoming, I personally also try to contribute to that front through my thesis and through my research work. As far as the AstroSat conclusion is concerned, right now as a field is active, because AstroSat was launched in 2015. A lot of science was done with it over time. Like I mentioned, there's a PhD repository for instance. But in 2020, a special issue was published by the Astronomical Society of India. It's available online, which is why I thought of covering it here. It's a collection of articles specifically again focusing on what science was done with AstroSat. There is more science because not all papers have to be published here itself. They get published in other journals also. Lucky for me, there were two chief guest editors who had been invited for this issue. One of them happened to be my supervisor. My article naturally went to the second one, and that person is known to be the inspiration behind Vijaya character in the Nation Number movie. So in my inbox, I could see a good collaboration between a highly experienced phase of space science in India, along with a highly experienced phase of higher energy astrophysics in India, coming together and joining hands towards a common goal of working towards a common article. Again, a lot of the AstroSat software which is used for analyzing some of this work has been developed on top of the existing NASA software. So it's not standalone, like I said, astronomy remains a collaborative effort. So all the articles that were published in this special issue also ended up featuring on the NASA website. This is an introductory infographic which I have prepared in order to better communicate the work that was done. I will not go into the details of what my work was, but if you were to focus on some of the middle two telescopes here, then they go to show that why X-ray astronomy space-based telescopes are a must. You cannot do X-ray astronomy simply by ground-based telescopes. I'm putting up the slide from my PhD defense, but what I would like you to focus on is the bottom line where I've enlisted some of the acknowledgements. That which again go to show that a lot of the work which is done by grad students can only build upon some of the previous work which your faculty members or older or more experienced people in the community would have already done. So a lot of software development, telemetering the data from the space telescope to the ground, it involves a lot of process when your instrument is out there in the space. The key one I wanted you to focus on is the fourth icon, which is the AstroSat cell. This one is dedicated to AstroSat again, but there was a specific space in Ayuda which was dedicated to this, and you could see some of the some students over there working on it and making some preliminary analysis. Now that Aditya L1 has been set up, there is a separate space dedicated to Aditya L1 also, which has joined the AstroSat effort. To give you a quick feel for what these instruments do, on the left, there are the preliminary pulsations that get recorded in a detector out there in space before they are analyzed or anything. Because I deal with pulsars, you will be able to see that it's a pulsating flux. And on the right, if I were to not see the data as is, but if I were to see it how the data overall behaves on a long-term scale, then you will see that the flux first increases and then it goes back down, decreases, which basically means that the pulsar is coming towards us and going back again. So even that motion is pretty visible in the data. The flux is higher when the pulsar is even slightly closer to you, and then it recedes when it goes back away. Primarily because I was dealing with sources which were like binary accreting X-ray pulsar, which means that the pulsar revolves around the second compartment. I can also present some details on the insect image which is there. That image was presented in 2002 Nobel lecture by Ricardo Giacomi when he presented the merits of X-ray astronomy to a much larger global audience. And he also happened to choose the same pulsar which I had, so the pulses are expected to like match, and I can verify whether they match. Again, I will not ask you to go into the technicalities. I have included these slides simply because I want you to get a feel for what the real work looks like, what students might be expected to do. Sometimes I remember Nabadana used to say your x-axis and y-axis is not labeled properly. Believe me, it sounds like a very trivial thing, but in my review also I had to write this. If your x-axis and y-axis are not labeled properly and you're working at this level, it does become a great point of comparison. So all these things do matter eventually, and you're expected to just take care of them in the longer time. That's why I have included some of the technicalities, but I will not go into them for the sake of this lecture. Something that I wanted to show is the Doppler modulation formula. That's something that we do in 12th. I also saw Doppler effects in a GK book on physics, for instance. And it was good for us to check how this formula was actually able to, we were able to apply it to the motion of the compact star around its binary companion, because it comes towards us and then goes back again. So we were able to sort of see that the pulses were slightly blue shifted when the pulsar comes at us, and then red shifted when it goes back away from us again. Also, something that I can provide details into is how the collaboration works. After I presented this talk, once the paper is published, we received independent confirmation on some of the findings which we had made by different groups in the states. And then the same work was extended by another group at IIT Bombay who presented their own paper later. And it was also cited by a group in RRI, which is the Raman Research Institute at Bangalore, who had a group which was very specific to this particular research area. Next, now I want to get out of AstroSat, because after having presented the AstroSat, anybody in the high energy astrophysics can now tell you that now we are looking at ExpoSat. Our faculty members in our group meetings are asking us to start attending lectures on polarization and start taking workshops on polarization, because now this is not just the Indian space astrophysical trend. It happens, although it is the Indian trend, it also happens to be the global trend as far as X-ray polarization is concerned. Now, why polarization? Polarization, X-ray polarization specifically, has long remained a technological challenge. So, irrespective of how advanced you were, people were not really able to realize such telescopes, although they were theoretically proposed in some earlier literature. So now there will be it's a coordinated effort between all the countries right now, and they have divided the X-ray band. The mid X-ray band, for instance, has been given to the Indian effort, and all of them will be sending satellites up together. So this is part of a larger effort. One thing which I can highlight from here is that the Vijaya Plus paper was another landmark discovery with AstroSat, where they were able to do some X-ray polarization to a limited extent very early on with a non-polarization instrument. So that also was, that became a landmark paper again globally. As far as ExpoSat is concerned, a lot of the faculty interactions or faculty talks are now speaking about ExpoSat, XP, AX, XIP going up. XP was launched recently, so was ExpoSat. But this will be a series, you can expect a series of news coming out that different countries will set up their own X-ray polarimeters. This was again, I think everybody would now be expected to at least touch upon it if you are going to formally work on it. I had to put that in my thesis proposal as well. And to give you an idea, right now, if you were to think about any band, for instance, any observation you're making, the simple observation we make is this star is over there, that is imaging, for instance. If you were to look at how the flux is varying with time, so that, like in case of pulsars, if the flux varies, like it grows in brightness and becomes dim again. So if that kind of studies you are doing, it's called timing. If you are going to build the X-rays in frequency or energy, say, where you are now locating what the spectra looks like, it's called spectroscopic studies. So timing and spectroscopy has been heavily done. In my case, pulsar the compact object, so imaging is not available for it. But polarization can add, when you see how organized that light might be, and that can give you even more detailed information about the physics of some of these systems. Therefore, they are actually expected to not just add one but two new dimensions to the parameter space, where you can measure the degree of polarization, and along with the degree also the angle of polarization, which is why I often sense a whole other level of excitement around X-ray polarization. To get out of the X-ray zone, although X-rays remain the people who are most motivated about space because ground is not available to them, I want to get into the gravitational wave band now. to give you some idea. LIGO everybody knows, so that I will not be speaking about. LIGO is graph based. Something additional that I wanted to speak about, which is in its very nascent stage right now, but because it's called frontiers in physics, I thought I should be touching upon that. Is there are also talks of having space-based gravitational detectors, but given that LIGO India is still underway, this is in its nascent stage. So there will be, again, it's a global frontier. India is slightly behind, but there have been global talks of having space-based gravitational wave detectors as well. You will hear things like LISA, DESIGO, Yango, and India is trying to put forth one on its own. The primary, like in the electromagnetic spectrum, you have the X-ray band, which is most promising in space, therefore are the first people who are most enthusiastic about space. In gravitational waves, it is the decihertz band, uh, which would be the most excited about space-based telescopes, because those detections cannot be done with ground-based telescopes. It was my assignment to cover some of the science potential with greater depth in one of our topical courses. Swarnim recently was asked to contribute a paragraph on how his expertise or the field that he works in might benefit from space-based. And then he was again able to refer to my assignment, but it's in a very nascent stage. So I'll give you some idea about what kind of work goes into this at such an early stage before it's put forth for government approval or before any white papers are released, after which it can be public knowledge for the news, for instance. Again, I'm going into these details only because for us it's academic purpose, but at such early age you have to worry about what kind of future challenges would be encountered if you were going to put forth such a vision. The science community already knows from the science point of view why they want to propose something of this sort, but because you are able to put it for approval of the required funding, sometimes there are a lot of challenges that you have to think about as to how you are going to justify this. In the space-based front, like I said, Visa, Tiango, and now the Indian front is proposing something. Right now it's called as GraphSat. It might also get called as EWSat. I've included here the bottom screenshot. If you see, I'm only stats for minutes of the meeting, not to be confused with Mars orbiter mission. So those discussions are still going on, basically, and it goes to show some of the early efforts that need to be put in before you can present a more confident proposal to begin with. I won't go into those details because I will leave that to the PIs or the faculty members to go into the details, but you will still, students do end up contributing to all of this in their own perspective. So, for instance, the way we have designed our theses is they are slightly mutually exclusive and exhaustive. So we hope to span the full map of physics through our thesis. So some of the work which I don't end up doing, for instance, he ends up doing. So between one of us, it gets covered. The GraphSat thing, for instance, I was asked to give a presentation, but in his case, he recently had to submit a formal write-up, which will then go into one of these white papers. Something else, now this is an international telescope. I only included this within Indian astronomy because some of the people who work on this might still, because of nationality, like some of the people might be Indian. We were given assignments on this, and we, despite being Indian, we were trained on how to be using these satellites as well. Vijaya is completely state of the art right now, no ifs and buts over there, and the main purpose of Vijaya telescope right now is to perform astrometry, imaging measurements of which star lies where to a very high precision. And everybody in the community is completely one of this, that Vijaya measurements are completely state of the art right now. Another thing that has been proposed, so it's not in a very nascent stage right now, is the CND Bharat mission. This is, I'm coming back to the electromagnetic band, and this is not X-ray. After the COVID, WMAP and Planck missions, India has thought of, once the success of AstroSat was demonstrated and your capacity to bear such a responsibility has been demonstrated, there were other people again who were lying in wait and who said, now we want to go to space. So this was one of those communities, and the CND community has put forth and has approval for its own dedicated mission, which it will contribute from the Indian side now. We call it CND Bharat. Aditya alone, I personally have not contributed, which is why the slide comes slightly towards the end, but I do not want to take away from its significance. Another thing you should note about Aditya L1 is that it is not specific to a band, it is specific to an object. So it will study the sun. I think that one of the recent NSD teams has also been specifically dedicated to Aditya L1, and a lot of work is being done on this front as well. There are two more missions which I can definitely think of, but I have not had the privilege of having to contribute to them yet. But Daksha is one. It is being led by Varun Khalera, who is also a Fergusson alumni and is currently at IIT Bombay. He has special permission to fast track this mission, and it will look at electromagnetic counterparts of gravitational waves. So that is one mission. And second, again something which is being spoken about, which I am aware of at my end, but it is not very out there yet, is there can be an AstroSat 2, because once X-ray polarization capabilities have been demonstrated with XPOSat, these people are planning on having a polarimeter on board for all X-ray missions that ever go up henceforth. So they will just do everything in one payload itself and try to make it as multi-capable as possible. So AstroSat 2, and you might also expect more, like some people are also saying X-ray polarimeter probe or something of that sort. Once, it's a step-by-step thing. Once some success has been demonstrated, you get more approvals for more advanced missions. So all of those are on the line. If anybody is interested, then this is an excellent article that I came across. It's in that special issue, and it's formally put forth by ISRO officials as to what other missions are in the pipeline on the Indian space astronomy. Two more places where you can look at if you might be interested. One, the Indian Mega Science Vision 2035 was recently finalized and made public on the, I think it was the EST website. And although Ayuka is the leading author on the front cover, this has been a grand endeavor across all the astronomy institutes in India, where all experienced and young astronomers try to contribute to having a larger vision by 2035, what can be done. Second, you can also take a look at the International Astronomical Union websites. Again, like I said, astronomy necessitates collaboration. So this has been a very early effort, and that community has grown a lot over time. They have now divided themselves based on their areas of specialization. Division B, that deals with high energy astrophysical phenomena, or subsumes an old division on space. Again, goes to show how much high energy requires space, but also the other way around. To give you an idea about some of the frontiers on the research front, astrophysical inference front, the field that I specialize in being pulsars. Right now, because we do not have imaging available, what people have been able to do is using timing and spectra to map out the surface of the neutron star, and a lot of statistical analysis is required for that, to an extent that just to be able to remember that a neutron star is only about 10 kilometers in size. So, and it lies at a very much larger distance. So, in order to be able to do that, just by seeing how flux is varying, for instance, it's a very commendable feat. Recently, an entire special issue was dedicated by the Astrophysical Journal Letters, just discussing some of these findings, to give you an idea about what's happening on that frontier. Another thing you will hear about is theoretical endeavors and data endeavors are now being slightly subsided, and it is the age of computing. So students are being encouraged to see workshops happening on computational astrophysics, simulations across fields, because with the age of computers, newer students are now expected to perform more high-end computations, for instance. And, mathematics-wise or data-wise, whatever could be done, the best of it might be behind us. I'm not ruling that out. But a lot of scope still with computers is still remaining to be explored. So there is some impetus for that kind of research as well. Now going to the bottom, where I will start off from where we lie as students in all of this, because sometimes it can also sound daunting. How will we be able to, it sounds a bit distant to us. To give you a, school students might know about, or do know about black holes and all that, so a rough idea. I mean, they might, we don't really have depths of knowledge into the space frontiers as much, only the ones which is available in public readily. But astronomical objects people know. So the ones that I was interested in primarily and also explored initially during my UG physics was X-ray pulsars, for instance. So like black holes, stars, novae, nebulae, and other classes of objects. Pulsars lie close to black holes, but they're slightly less massive. They are compact objects. They are called neutron stars, and they emit beams of light in the X-rays, and they go around. So like a lighthouse, whenever that beam points at us, we see a growth in the flux. Like we see it to be very bright, and then when the lighthouse again points away, we see that the source has become dim. Sometimes these fluctuations are intrinsic to the source, like the source itself might be growing bigger or smaller, but this has a lighthouse kind of an effect. The image on the left is by far the most accurate artistic depiction of what I've come across. All of these inferences about the details of that image have been made purely through observations and physics inference. So the more we know about physics, the more details we are able to infer about the system. Imaging is not available for them, so you cannot just directly see it. A lot of my work ends up having to deal with artistic impressions. A closer idea is material is accreted from a secondary star and it gets obstructed at the magnetic field of the neutron star and funneled onto its magnetic poles from where the beams originate. Now, moving slightly up into the technicalities of the topic, something that gets covered in 12th grade is your cyclotron mechanism. Basically, the charged particles rotate in a magnetic field. So that kind of stuff does actually happen out there in astrophysical scenarios as well, where this accreted material ends up being a plasma, and then it moves in the magnetic field of the neutron star. So a lot of my work ended up having to deal with these cyclotron energies, for instance, where I have to take into account the resonant frequency of rotation for which we have formulae and we are expected to apply them even in UG later on. The X-ray polarization front, which I said remained a technical challenge for a long time. The one which India will be sending out is the Bragg scatter, basically. And that scatters X-ray polarization in a way where, depending on its initial degree and angle of polarization, the photons are scattered preferably in a certain direction, and that's how they're going to infer it henceforth. Third is from my nuclear physics textbook. The principle of operation for a Geiger-Müller counter remains the same as the large area X-ray proportional counter on board AstroSat. The pulsations which I initially showed you before in one of the earlier slides, that was the raw data from the instrument that is basically detected in this instrument. Any incoming X-ray photons generate secondary ionizations that get recorded as a current in the external circuit, and any students who are hoping to then work on this would be expected to be familiar with some of these things so that more advanced stuff can be done. On the left again, I have a screenshot of something, of a part of my index in the thesis. If you notice, it's in the same format, like formula, diagram, algorithm, flowchart, which used to be there for our computational practicals. Because it's numerical simulations are being encouraged, I was also asked by my supervisor to try to stick to as much computational astrophysics as possible. However, if you see, some of the top lines correspond to coordinate systems. So I had to construct polar coordinates, spherical coordinates. I also had to have an opinion on what would happen if we were to use cylindrical coordinates. So that is again some kind of stuff which I had to explore. There used to be a practical of Zeeman effect where we had to modify the magnetic field, and there was a source of light in mind, and then you see how some of the physics is vary. In my case, the setup was fairly similar, but it was astrophysical in nature. So my electromagnet was made up of nuclear material, and it produced a magnetic field of 10 to the power 11 to 10 to the power 13 gauss. I had to vary that. And my source of light was a polychromatic X-ray source of light, emitting at about 10 to the power 7 Kelvin. So I had to vary that range. But the exercise was still the same, and I was able to derive from that practical a better understanding of what I would be expected to do in these scenarios. Moving on to PG, I had given a presentation on pulsars, if I remember, detection of neutron stars pulsars. So that was a concept which I had been expected to cover in my class. These are some of the slides straight out of that because I found myself referring back to them when I was working on these now myself. I was pretty happy to see that I've already covered Exposat and therefore I was pretty conversant with some of the basic concepts which I would have expected to be known. To give you a feel for what might be expected at this level is this is a derivation which I had shown on my slide, but then it again got asked. I was fortunately in the INAT exam, and then I also found it in a very standard astrophysics book. So just to give you an idea about what kind of, it's not very involved, but it tests your basic understanding about these systems and whether you've given some thought to them. So that is the depth to which you are expected to probably have gone to before in the initial stages of your graduation. I didn't know how to put this slide because gravity is a UG plus PG effort, but both of us had participated in UG. When we had come to co-inaugurate gravity a few years back, I had mentioned when I had visited here that I am finding a lot of the work that we did in gravity was directly useful in my PhD, and I'm going to back that up today, which I had not been able to do back then. I was not bluffing. So, beam emission from pulsars required me to have heavy knowledge about beams itself. Was like my exhibit had been Tyndall effect and scattering of light. So I was using laser beams and I was showing how they were going about and how you can track them because it's a scattering medium. Whereas so I didn't have done stuff with polarization and I had to put the two together basically. I was dealing with pulsar beams which are astrophysical in nature but equally pointed and they may not have coherent emission like a laser, but I still had to be dealing with those beams. And the reason why they were changing direction is was gravitational in their nature, but I had to track that. And eventually I had to go deep into them enough that I had to track some of the polarization status in there as well and comment on the final polarization. That's how it got put together. The details of having to do this required me to actually deal with differential cross sections in my calculation. That is what the real work, like groundwork looked like, which is often not shown in general public talks or National Science Day posters, for instance, because it can get too technical. But lucky for me, I had happened to give a presentation in my UG exactly on this, and it was quite a lengthy derivation, but I was able to see how the formula for differential cross section, which was a simpler formula back then went on to become a far more complicated formula. But the spirit in which these exercises had to be carried out was pretty similar. And I characterized it under PG because the then head of physics had asked some of the master's students also to attend it. So although I was in UG, it was delivered to a UG plus PG audience. Going back to my PG physics or my Pulsar's lecture, some of these concepts get covered here and there. And while we're doing it, we don't really understand the significance of it, but later on, you're just expected to know it. As if you already knew you were going to specialize in this. So what I can do is from the vantage point that I am at, I can show you, I can now connect the dots backwards and see what was essential for me. So some of the things that were covered in experimental techniques, for instance, time domain analysis, frequency domain analysis, autocorrelation, cross correlation. There were also radiative processes in physics that got heavily touched upon later on in my thesis. And that had been covered in my summer school when I was at Ayuka. Something that I wanted to, again, the practicals in astrophysics again are very useful in improving our understanding. It remains something which is very out of reach and not available in other universities. And something Wien's law I wanted to specifically specify because if I say that my polychromatic X-ray source is emitting at 10 to the power 7 Kelvin degree watt, it's basically of the order of the core of the sun. Kind of a temperature, but it's a bare core. So what happens is, if you apply Wien's law, then the peak of the corresponding black body spectrum naturally falls in the X-rays, and that is how that inference was made. So again, goes to show that while we are doing this in textbooks, it doesn't really sound that profound, but astrophysics does present to you physics of extreme physics and extreme astrophysics where all of these concepts can then be applied, have been applied by people who came before us to get more insight into the objects. And now whatever we know about this is because of our understanding of these physics concepts. Again, there has been a focus on encouraging interdisciplinary research. So, computing, for instance, especially in Python, using different packages, has been encouraged. I myself was able to draw parallels with some of the research interdisciplinary exposure which I had before my PhD to my BSc project, MSc project, or some of the other courses which I had taken, which may not be obviously related to my field, but helps you connect the dots between different fields and integrate your way of thinking about a particular topic. Something that I wanted to highlight on the interdisciplinary front is one, econometrics was again one of Swarni's assignment, and his co-supervisor at Ayuka also had encouraged people to take up a non-obvious physics topic. So econophysics kind of put economic science and physics together. And second, biomedical was an extra credit self-study kind of a course which again helped me add more to my perspective of how I come on a topic. Progressing to graduate texts now, PhD level, so this might be slightly higher, but you will see that it may not be as scary. On the left, I have a recent textbook that was put out in the GR and GW track. So right now, GR, GW, if you were to actually look for any references, you will end up being recommended 10 to 15 different references and you get lost in there somewhere. But thankfully, they came out with this sort of a textbook that can hopefully be what goes is to NFD. But in there, for instance, they have a subsection on gravity and curvature of space-time, where the first one is gravity bends light waves, and second is gravity affects clocks, gravitational redshifts. So both are these things which I tested for pulsars, and one of my chapters is dedicated to this. And secondly, on the NLP and computational front, Rangmanch integration and Gaussian quadrature, for instance, was something that I had to look into for my single author paper. So you're not expected to know all of this, but you're expected to have a certain level of understanding that you are able to work with whatever might be required on your research project. And this is the most advanced one where your textbooks take you to. This is where, for instance, you will see cyclotron radiation, plasma physics. So this was more astrophysics heavy textbook. So I also ended up citing one of them in one of my paper. So that's how some of the work eventually goes to the research track. Final two slides where I will try to put together and merge where my two sections of the talk come together. The first one is Cosmic Varta, is a graduate student driven endeavor. So like frontiers in physics is by far of physics, by far of students. Cosmic Varta is again by far of Indian PhD students in astronomy and astrophysics. They have maintained their own website. It's slightly different though. You will have seminars. They try to come up with popular science articles that explain some of the work which students are doing. Either you can contribute to it in first person. I was falling short of time, so I only to write an article on my own. But if you see, this becomes sort of like a hence-proof kind of a slide, because when I was making this presentation, I saw that the top 3 featured articles on their website. Although everybody works on completely different topics, astrophysics is a huge field, as you would have seen by the range of talks that have been held over the past few days. All the top 3 topics were dedicated to Indian space endeavors. That just goes, which is helps me justify that what the talk I was giving was not just because it was specific to me and truly tried to, from my end, do justice to the purpose of this platform and event. And secondly, the last time I was here, both of us received our degrees from during our convocation ceremony. Again, to put it in a big picture, both of us received books that tried to put Indian science into perspective, like we have the Mega Science 2035 document. Back then it was the India 2020 vision and so on. And there again, within those books when I read, with a lot of foresight, there were projects defined in the long term where would India need to progress in terms of its science, with Indian needs in consideration, and over the choices of our careers with our electives and all, we tried to be there. It helped us pick or specialize in topics that would help us contribute on that front. during our education itself, so as students. So yeah, this was my last slide. I think I have delivered whatever I've been able to, whatever I've been intended to cover. So, yeah, based on the questions we are going to the okay.
Thank you, ma'am, for your insightful talk. The floor is now open for questions. So, ma'am, there was one slide where you mentioned pen versus pencil. Could you tell more about that?
I was slightly hesitant about going into those details because I didn't know whether people would be interested in that. It's literally the heart of my teaching, so I can mention. And it has been a long-standing problem again. I myself was pretty surprised to find it in the 21st century, especially when nowadays people talk about quantizing gravity. They don't even know pencil and family. But the way this problem is defined and has stayed so far is when the lighthouse is basically going around. We still don't know. So we see the rise in flux and then dip in the flux. But we still don't know yet because based on the physics that has been inferred, there are two possible mechanisms, both of which can produce a similar observation. One is, I think go to that slide. One is the beam can point along the magnetic field, and therefore it emits. That is one kind of beam which is possible. That is like this, basically the beam which is shown, this kind. And then if the pulse is high, then the beam is pointing right at you. So your rise in flux basically corresponds to 0 if the 0 pulse are pointing straight at you. But there is a second possibility as well, which is known as the fan kind of emission, where the emission actually comes perpendicular to the magnetic field because of the way some of these scattering processes take place very close to the accretion region. And therefore, if it is perpendicular, if it is pointing right at you, it's going to give you a dip in the flux which is very counterintuitive. So astronomers still don't know that if your pulse is basically getting recorded as this, whether the top point corresponds to the pulsar pointing at you or whether it is pulsar pointing perpendicular to you. That is what I mean by the pencil and fan beam regeneration. You see there are two diagrams here or even a comparison here. This is the beam pointing along the magnetic field and this is perpendicular what you would typically have in the lighthouse. I have even tried to show a comparison with the Eiffel Tower, so just to give a better idea. And X-ray polarization is supposed to resolve that because the two scenarios are expected to have completely distinct polarization signatures. So even if your flux is going and reducing, that will stay constant. But now with added information from the polarization front, at the peak what polarization measurement you have and at the decline what polarization measurement you have. So both of these put together can help you resolve what kind of a mechanism is responsible and then it will help resolve this long-standing problem. Yeah, if there's anything, you don't need to have a technical question. If there's any particular slide that you found interesting that you would want me to go into the details also, because the slides are available right now. That's what
very nice talk. I just wanted to ask you, can you elaborate more on the decimal's gravitational waves you mentioned? Because I heard that pi 70 one of those colloquially measured was something.
Yeah. So he is the person who's leading this. He is the one who gave me that assignment. And even when I was doing that assignment, but it goes to show again how your individual assignments again contribute. So if I had taken it in a pass or fail kind of a spirit, it remains specific to my mark sheet. But realizing the purpose behind this, I ended up giving a 45-minute presentation, and I was also quite pleased to see that he was also able to refer to that presentation eventually, long after that assessment was done, and now contribute back to that mission again. Although I may not be able to do so immediately, I contributed to it in this way. So Sanjay himself he's proposing this graph sampling, and this is something, Yango is an American from Chinese collaboration. They're obviously far ahead, so you can use that as a reference to try to see what might be useful for the Indian front and also doable. Okay. So Tiago was that, and because the decimal band specifically is very promising from the point of view of its science potential. If you see, for instance, this diagram, it samples a long, like terrestrial lie somewhere here, LIGO, but a lot of objects fall exactly within the decimal band. So your exciting science, once everything has been, your capacity has been built, your expertise has been demonstrated, the real science, promising science lies somewhere in the decimals band. And they will eventually, like Astrophysics try to do multi-wavelength in the high energy band. These people would eventually like to go to multi-wavelength gravitational wave astronomy as well. But again, because life is still underway and still a long shot, this remains in a nascent state. But that's what these people are wondering, because you also have to think about remaining internationally relevant. Otherwise, it still remains a futile exercise if you're not able to contribute to the international level paper again. Again, here if you see, currently the LIGO community talks about the LDK collaboration, so LIGO, Virgo, Kaka. But Sanjit was here, for instance. He's wanting to propose GrabSat. His son also drew a diagram during my presentation and called it GWSAT, so he might just change that name. But yeah, he had me referring the Tiango effort first. Desigo is again something, if you saw a later slide, I had in his textbook, there is a section on space-based detectors, and that in this Desigo again, millihertz would require these, and that's a separate thing. But decihertz remains a very processing thing, and it would need space for it. And that's why some of these initial meetings are going on as to what can be done with this. This Tiago again, if you see, one of these co-authors later visited IIFA. And then I was able to send these slides and my assignment material back to this guy, so it also acted as feedback for him as well. But yeah, that's where the decihertz is. I was skeptical about whether I should cover it because I shouldn't be revealing too much too soon as well. But grad students do get it, so get that kind of information. So I just thought I should touch upon it for the sake of completeness. But this might, once it's been more formalized, the way it goes is that they will apply for approvals, and then they will come up with a proper white paper, and then that word or whatever name that they will decide for it will eventually trickle down into the future sections of textbooks. And yeah, it remains a long term.
Any questions? Parisee, first thing, thank you for taking this topic of using physics. I think you have covered most of the things students would have liked to know as they go from UG to PG, whatever they're learning in their BSc, MSc. Sometimes, as you mentioned, they don't realize that this can be useful later on. So, yeah, this was a different talk, and I'm sure everybody has learned something from it rather than covering one topic. You have included everything, what they should know, and how that could be utilized somewhere in the future. So, really, congratulations for that. And one more thing, I wanted to know about your single author paper.
That happened because I myself found something. When they asked me, okay.
At least maybe the topic or the title.
Yes. So it's slightly theoretical based. The three gone factors for atmospheres and accreting pulsars observable with X-ray space missions. Our aim was to go towards future space missions like ExpoSat and something, but while doing some of those calculations, we saw that gone factors might be needed as pre-computable quantities that can go into the eventual code which I would be expected to develop. So I computed gone factors, but when I was computing gone factors, because I got interested into them, I kind of read more about them. I saw how people who specifically study gone factor study. And then I was also able to write more codes into going into that direction as well. And one thing led to another, and we were able to develop it into a full paper. Again, the astronomy and our goal still was to still do it from a polarization point of view. But because I was able to make some progress on that front as well. We still thought maybe she can submit this to a journal because it might still be an addition, sizable addition to the existing literature that we have. And because these quantities will be required, it's again very difficult to come across people who will be willing into those kind of depths as well. There are other papers, for instance, if they wanted to model polarization characteristics, they will just apply gross analytic approximations in order to make progress by leaps and bounds. So if somebody has shown the readiness to go into that kind of detail, then the reviewers are also happy with this. So they thought this could be reported and then it can be used by other people as well. And I've actually also developed this irrespective of pulsars, it is cross-linked with just plasma physics as well. Like I said, if I draw parallels with the xenon effect practical, then it is a measure of how your plasma itself behaves irrespective of whether it will be of where your X-ray community stands at. So yeah, I also have a separate poster which I might present at the conference, so from a purely plasma physics perspective. The focus here, however, was to study three bond factors. Bond factors are they are a very fundamental quantity in how the photon plasma interactions behave. So the interaction of the X-ray plasma with the photon particles. They typically go into the computation of stellar opacities and optical depths. And PP characterizes Bench-Talon processes, which is why in one of my later slides I had also circled the plasma physics and Bench-Talon chapters because I had to refer both of them for this paper and go to greater depth. Bond factors can be computed for all kinds of plasma interactions. In my case, they were PP. They were also anisotropic in their nature because, so again, a type of bond factor which I was reporting. The presence of the magnetic field resolved the bond factors to be resolved into two components. So their interactions behave differently along the magnetic field and perpendicular. So all those kinds of details. And again, like a specific conditions that we had were not local thermodynamic equilibrium. So I think it just fit into a publishable standard. I thought it was significant. The reviewers were also happy.
Good. Can I have Swami who is around here? I would like to ask both of you a question. Swami also was a BSc student in our college. Later on, you were talking about your MSc, right? Both of you are brothers and sisters. So, how do you kind of work together? Because I've seen you talk that he's going to take up some things, and as brother and sister team, as Fergussonians, impressed from the astrophysics, both in Ayurveda, one finished PhD, one doing PhD. So, what kind of things do you discuss as astrophysicists and as brother and sister, as a team? I'm sure it's not sure if you can help each other in whatever work they're doing. Your work, maybe she's helping you.
Yeah. So it's like sort of complementary. Interestingly and coincidentally, so both of us work on pulsars. So the thesis has pulsars in it. My thesis talks about neutron stars, which are same thing. Just that pulsars is something you observe as pulses. So it is complementing in the sense. So my work focuses more on the interior parts of it. So what is inside the neutron? So all of the things that she showed, like you're getting pulses and the bond factors, like how does your photon travel through plasma? These are all atmospheric effects and something that happens outside the neutron star or neutron star atmosphere. And the second part of it is going inside, which is not directly observable, just like sun. In the case of sun, we observe the photosphere and a bit of chromosphere, but we don't know what is inside. So somehow we want to connect what we observe on the outside or on the atmosphere or exterior of these pulsars and connect it to what is there inside the neutron star. So this is how it gets connected, and she works on these external effects.
And in external, I work on everything that can go wrong in the external, which is why binary accreting X-ray, because you also have a normal rotation power pulsar. But binary accreting X-ray pulsars gives you the full variety of what can happen in the exterior, whereas this topic again gives you the full variety of what can go wrong in the interior. So that's why I said you tried to select the facility.
Well, since you got to select off the paper, is there any chances of you two publishing a paper together?
Yes, we do have one.
Only two of you. No.
Yeah.
It's just that was a coincidence though, because people sometimes think that it was already planned because you cannot force these things again just because you happen to be, it still has to be substantial in its content. But luckily it just so happened that his supervisor happened to assign him a particular project because she has several grad students, so there's no reason why she has to assign it to him. But what he got assigned was directly related to me again, so it just officially was also just kind of being a very natural to be. So we do have one out on archive. I'm awaiting the referee report for that. On the case. Just because you asked on the UG-PG fact as well, I just felt that extra sense of responsibility as alumnus again. Other speakers may or may not cover it, but having been on this side as well, I just felt that natural sense of responsibility for covering those grounds for the students.
Thank you, ma'am. Thank you, everyone. I request Rakata Madam ma'am to present the memento to Dr. Shirke as a token of our gratitude. We have the members. We will now take a short break for the refreshments, which will be served outside the amphitheatre. We will resume our session by 4 p.m. Please be seated 5 minutes before.
Remains a very constructive exhibition of one's power and can only give rise to healthy competition, if not engender a sense of awe, admiration and respect.
The new construct. So this is how it gets connected, and she works on these external effects.
And in external, I work on everything that can go wrong in the external, which is why binary everything external, because they also have like normal rotation power Pulsar.